Okay, welcome back. So now that we have a general idea of what modules are and all that about Verilog, we will start with the software that we can use to actually convert our Verilog to a circuit, which is in this case Quartus. So I'm on an ECF machine, okay? You just fire up the start menu, type Quartus and you will find it right away. Now the next bit is important. Every step along the way of creating a new project actually affects everything later, including the fake FPGA and many of the mistakes or many of the errors or the issues I've seen people have were actually caused by things or could have been mitigated by things in during the project creation. So let's create a new project. First of all, the location for the project. So you cannot save anything on the C partition. It's not persistent, meaning if the machine restarts or anything happens, you will lose all the files that you've saved on the C drive. So you cannot save it on the C drive. It is tempting to use one of those quick access things, for example, the downloads. But just to show what's going to happen, let's use this. The path here starts with / service homes, $, blah, blah, blah. So all of that, this causes Quartus to go haywire. The special characters are not supported by Quartus. So the project will create fine, but during the compilation or at some other advanced stage, Quartus will suddenly complain saying, hey, I cannot find this file or I cannot save this file or so on, and you will not be able to continue. So the correct location to actually save a project on the ECF machines is this W partition. This is a persistent storage. It's persistent across reboots. It's probably also persistent across different ECF machines and so on. So this is where you should be creating your own project. So I'll create a new folder, which I will use for my project. Oops. Okay. And now we select this folder. Now the name of the project, just give it a meaningful name. And then the third option is what is the name of the top level design entity for this project. Depending on the part you're working on, it should be part 2 or part 3, but we shouldn't really change it in this stage. The reason is when you change it in this stage, it will break the compilation script for fake FPGA later. So this name for now, this name has to be exactly the same as the project name. Please do not change it. And the other thing is they cannot be main. So this is wrong. Okay, so it has to be some meaningful name, same as the project name, not main. Okay. It's an empty project, yes. Now we are also, if you have already created your files, you can add the files here. I have already created my files, but I will not add them now. Picking the device or the board could cause issues if you pick them wrong. And the reason is because the pin assignment we use is specific to our board, which is the DE1 SoC. So if you pick another FPGA device, this is actually a big list, you just can't see it, yeah. So if you pick any other FPGA device or if you pick a different board, you will get errors while trying to compile because the pin assignments will be incorrect. You don't need to modify any of this, and we're done. So now we have our project. It's still empty, there is no files. You can start by creating new files here if you want. You can press new, you'll find the Verilog HDL from this menu. Of course, as I said, we already have our high level, I already have my pre-made files, so I will just add them. You can change the view here to files, then add remove files in project. I have my files here. Let's add those. Okay, so now just a reminder, this is my smaller module, which is a MUX221, and then MUX421 is my top level or my top level module, which includes instances of MUX21. Now you have to specify that this is the top level entity, and then you can compile right away. Once the compilation is done, I'm going to show something useful. It could help to visualize the circuits you're building by seeing the schematics of them. For example, we'll have to wait for this to finish first. So for complex circuits, this process could actually take up to hours. So those couple of minutes of wait is nothing. And we're done. So under this, there's a tab here, Analysis and Synthesis. If you open this tab, there would be netlist viewers, and then there's something called RTL viewer. This views your design as a schematic. So basically, after your Verilog design has been compiled, you can view the schematic of the design with its hierarchy, with all the levels of the hierarchy, and so on. For example, this is our top level. The inputs are switches, the outputs are the LEDs, and then these are the instances of the MUX21 inside our MUX41. You can expand the instances without diving inside them. This could actually be multiple levels of hierarchy, as I said. So you can view complex designs and make sure that the schematic makes sense, just to be, or just to help you visualize or understand the Verilog at this point, and so on. Okay, so we don't really need this. It's just for visualization. It doesn't do anything. So the design is actually completely compiled by now. The process, the entire process does the following. So analysis and synthesis takes your code, makes sure the code is correct, like the Verilog itself is legal, and then converts it to some sort of generic logic gates. And then those generic logic gates, during the place and route stage, depending on the actual FPGA, the tool decides where to physically place those logic gates inside your chip. The assembler basically takes all of that and writes it in a format that is called the bitstream format. This is what you can use to download your FPGA. Quartus is a tool for building or for compiling Verilog to something to bitstreams which can be usable in FPGAs. I've seen people misunderstand it as some sort of text editor. It's not a text editor. It's something more than that. Okay, you can use Notepad++ to write this code. Quartus isn't about the text editing. It's about the compilation. This entire list of compilation steps. Now that the design compiles fine, we should have actually verified it using Modelsim. I didn't because I know it works because I did verify before, but let's see how Modelsim does it. So Modelsim is different from Quartus in the sense that it is a simulation tool. It's a tool for you to be able to make sure that your Verilog code is correct, is functioning in the way you expect it to be before going through the entire process of compiling it. Because as I said, this compilation process can be very lengthy. It could take up to hours. And obviously if you've made a mistake and you wait until all those hours are done before you actually realize, it's just a waste of time. So Modelsim is a verification tool. Okay. First of all, we have to change the directory, change the working place basically to where our files are, and in this case it's in my W partition. It scrolls too fast. Okay, and in the W partition, let me show the file. We have here a wave to do. Let's check it out together. So do files are basically scripts that you can give to Modelsim to automate your testing process. So first of all, you create a library. This library is called work. This is a folder basically that Modelsim will write intermediate files inside. okay? And then you have to compile your Verilog files. Excuse me. You have to compile your Verilog files in all of them, every file that you will use for the simulation. In this case, these are the MUX221 and MUX421 files that I created. And then you tell it what the top level entity that you're going to simulate is, which is in this case MUX421. This command adds everything, all the signals inside those modules. It adds all of them to the simulation window, which we'll see later. And then this group, or this group, each one of those groups is actually simulating a specific test case. So this one is setting all the inputs to 0, setting all the selects to 0, and waiting for 10 nanoseconds. Then this group is setting inputs 0 and 3 to 0, inputs 1 and 2 to 1, and picking the second input through the select signal and waiting for 10 nanoseconds. You can have as many test cases as you need to fully test your design. I just made two simple test cases so I can just show them around. Now it is time for us to actually run this do file. So this is our Modelsim. We can say do wave.do. Okay, now you can see the wave. First of all, before we look at the wave window, let's look to the left here. So this list has your hierarchy. This is our top level design, which is MUX421. These are the instances of our MUX221, U0, U2, U1, and everything you pick, you select from here, you will find the signals inside it. So those are the ports, those are the wires inside MUX41. If I pick U0, those are the ports of U0, and so on. You can, if you want, you can pick some signals and add them to the wave window here. They would be redundant in this case, but they could be useful for other things. So for now, I don't want them. Now let's actually check the wave window and make sense of what's going on. Let's expand it here so people can see. Okay, let's zoom out. Too much. Okay, so this period from here to here is a 10 nanosecond period. Okay, this is the first group of commands that we had. You can, before I go on, let's see, this is the switch signal. Remember that this is a 10-bit signal, right? And then this is the LIDAR signal, which is also a 10-bit signal. You can see that some of the bits are zeros. Each digit here corresponds to a bit. Some of the digits here are zeros and some are z's. And I will say what this means in a second. You may occasionally get a different format. That's because you would happen to have a different radix. So you could have this as hexadecimal, or you could have this as binary. In our case, we want it to be binary because we're looking at individual bits, so binary it is. If this format is annoying to you, you can probably expand them and look at each bit on its own. These bits have a value of ST0, which means a strong 0. Okay, so the first 10 nanoseconds, we've set everything to zeros. So all our 4 bits, the 4 bottom bits, 0, 1, 2, 3, are set to 4. The top ones, which are 8 and 9, are, I meant set to 0, my mistake. The top ones, which are 8 and 9, are also set to 0. You would expect the output in this case, which is the first lead here, lead 0, to be 0, and that is truly the case. Then the second 10 nanoseconds here, you can check it out, and you find that we have the select signal as 1, 0, which means it's selecting the second, so the output should be 1, which it is. Yeah, here. You can always use the numbers on the wave itself will be different from the numbers in this column. The numbers of this column correspond only to this yellow cursor. So however you move the cursor, you can see the actual values there. And I think that's it for Modelsim. And that's it for this video. Thank you.